The main goal was to confirm the equation for kinetic energy. So we set up an experiment that helped in answering the question of whether mass or height has a greater effect on velocity of a free-falling object. We hypothesized that the object's height had a greater effect than its mass, considering that potential and kinetic energy are the energies involved in free-falling objects. Using different mass balls dropped at different heights, data was collected that supported our hypothesis using trackers' data of velocity and from our calculated velocity from our pre-lab equations. We used the equations for kinetic and gravitational energy and set them equal, then calculated the velocities with the height and mass of our objects. To help confirm our calculations, we also used tracker software and were able to get 4 velocities to compare to our pre-lab calculations. Height was found to be the major factor in change of velocity, supporting that kinetic energy is directly proportional to the square of its velocity, while mass is also directly proportional but does not affect velocity in the kinematics equations. Relating potential energy with kinetic energy for a free-falling object has determined that height has a greater effect on the velocity of the 2 balls being dropped. This shows that kinetic energy is equal to 1/2 mass times velocity squared because objects maintain their kinetic energy in the system unless there is a change in speed.
The law of conservation of energy states that the total energy of a system remains constant over time, meaning that all energy present at the start of a scenario is the same as the energy present at the end of the scenario. During the scenario, energy can be transferred between gravitational potential energy, the energy an object possesses depending on its relationship from a defined ground point, kinetic energy, the energy of motion, and internal energy, which summarizes various other forms of energy, such as friction, heat, and sound. For our model, the changes in energy over time can be modeled with a system schema showing that an interaction exists between the ball and the Earth, gravity.
2 trials of the same mass were dropped from 1 meter and 0.7 meters. 2 trials with a heavy mass were dropped from 1 meter and 0.7 meters. Each of these experiments explain the kinetic energy equation by showing that there is not a change in final velocities when comparing the different mass balls at the same height, but there's a change in velocity when comparing balls dropped at different heights according to our calculations, giving us quality results to verify the kinetic equation. Mass of the balls are considered directly proportional to the kinetic energy product. However, there's also potential energy to consider, so an object's mass should not affect its motion. Because before the fall, there was only potential energy. At the end of the fall, there's only kinetic, which we're able to set these equations equal to each other. So the existence between kinetic energy and potential energy for this experiment allowed the masses to cancel out and not be relevant for this focus of discussion. For example, there was no difference in the final velocity between 2.6 gram ball dropped in trial 1 at 1 meter and the 29 gram ball dropped in trial 3 at the same height. However, there was a difference between final velocities when comparing the same mass balls, but at different heights comparing trials 1 and 2. This leaves gravity times height equal to 1/2 velocity squared, where velocity is a particular realm of the model in verifying the kinetic equation. In terms of experimental flaws, there is friction of error, which is a factor that we are unable to calculate, as well as human errors regarding video production quality for tracker software. Some of these flaws could lead to result in inconsistent data with our model when comparing our theoretical and actual velocity results using tracker, for example, where the final velocity can be affected.
There is a constant force and thus a constant acceleration due to gravity. So, velocity can gain its acceleration times time and thus be added to that of the gravitational acceleration, which means that the balls that experience a larger velocity spent less time falling compared to the lower velocity balls. Because before the fall, the ball had no motion, we know that there is entirely potential energy, and at the time right before the ball hits the floor, which we defined as 0, there is no potential energy and thus only kinetic energy. We are able to set these values equal to each other using the law of conservation of energy. By calculating the initial potential energy, we can calculate the final kinetic energy. Our data show that the calculated initial potential energy matches closely with our final velocities from tracker. However, the numbers are not exact. This is likely due to problems with the utilization of tracker, such as the camera angle being slightly off level or the data points not being perfectly tracked. Despite these small disparities, we were still able to confirm that the kinetic energy equation is in fact kinetic energy equals 1/2 mass times velocity squared.
In conclusion, the experimental data in pre-lab design supports the kinetics equation when comparing potential energy and its relationship to kinetic energy for free-falling objects at different heights. With this being said, free-falling objects do experience change in velocity, but their masses do not have much of an effect.